Hello and welcome to this video on heterocyclic chemistry. Here we'll be looking at a general strategy for heterocycle synthesis using cyclisation and dehydration. First, I'll look at the rate of different reactions for ring formation depending on ring size. So if we look at different sized rings, we'll see there's a massive difference in the rate in which they are formed. 5-membered rings are by far the fastest ones to be made, significantly faster than every other ring size that there is. Next we'll see that 6-membered rings are also fast, but then there's a significant drop before the next ones. For small rings, such as 3, 4, then there's a lot of strain to get the bonds to reach the desired angles required to make that ring. For medium-sized rings, so 7, 8, 9, then the reaction starts to be difficult because the opposite sides of the ring start to sterically clash each other. Then finally, large rings are difficult to form because there's just no driving force for those two ends to ever meet. So it's no surprise that all of the heterocycles we'll be looking at are the 5- and 6-membered ring heterocycles. When it comes to thinking about how to make these heterocycles, well, the main strategies rely on cyclisation of acyclic molecules and dehydration, the loss of water. So, how do we turn this into a synthesis strategy? Well, there are 3 key steps. First of all, we need to identify the key heteroatom in the system. Then we need to identify the backbones around it. Finally, we need to disconnect to give a source for that heteroatom and some kind of dicarbonyl species that makes up the backbone. Well, what does that look like? If we start off by looking at furan, there's only one heteroatom, that's the oxygen, and then that leaves us 4 carbons around the backbone. So if we look at the kind of 4-carbon dicarbonyl species that we'll need, well, that's a 1,4-diketone, and because a ketone already has oxygen atom in it, that means we don't need to do anything to introduce a different heteroatom. So this gives us the Pyrrole furan synthesis, a synthesis in which if we treat a 1,4-diketone with acid, we will promote enol-keto tautomerization. So we can see that in the enol form, the oxygen can cyclize round to form that 5-membered ring, remembering that the formation of 5-membered rings is very fast. And then the lone pair can assist in the elimination of water to give the aromatic furan product. When we're looking at these syntheses under acidic conditions, there are a range of different acids which will promote this, but one of them, which we'll see quite often, is para-toluene sulfonic acid, the structure of which is shown on this screen. You'll note that each of these steps is reversible. So if we go from left to right, then we'll need to remove water from our reaction, and if we want to go from right to left, we'll need to add water to our reaction. If we look at the reaction more slowly, we'll start off with our 1,4-dicarbonyl species. That's the 4 carbon atoms in the backbone that will make the backbone of our furan. Under acidic conditions, we can get keto-enol tautomerization. And the oxygen atom can attack the carbonyl to make the 5-membered ring. Finally, we can use the oxygen lone pairs to assist with the elimination of water, first forming an oxonium species, and then by loss of a proton to build the aromatic system. Remembering that each of these steps is reversible, that takes us from our 1,4-dicarbonyl compound to our furan product. So, if we want to consider a different heterocycle, such as a Pyrrole, analysing this shows our heteroatom is a nitrogen. We have the same 4-carbon backbone, and that suggests that we need some kind of aminoketone this time, which we will be able to get from a 1,4-diketone, the same as before, this time with the introduction of an amine. So, under acidic conditions, our nucleophilic nitrogen will attack the electrophilic oxygen of one of our carbonyls, and then we'll get an attack of a second carbonyl. This will build a 5-membered ring, and the lone pair can come in and it can assist the removal of water by making iminium species, and then loss of a proton gives us the enamine, and we can do that twice to build the aromatic system. Again, this is a reversible process, and again, it can be catalyzed by acid. If we look at it in a little bit more detail, we have our key 1,4-dicarbonyl species and our amine. That provides us the nitrogen that we need for our Pyrrole. The acid will activate the carbonyl so that our amine will attack. But then our amine is still reactive, and we still have acid, and we still have a second carbonyl, so we can get the second attack to make our 5-membered ring, which is a very fast ring size to form. And that gives us our 5-membered ring, and this double hemiaminal style intermediate. We can use a nitrogen lone pair to assist with the elimination of water, so it pushes in. We lose the OH, assisted by the acid. And then we lose a proton to give us our enamine. We can draw the exact same thing again, and that results in the loss of our second molecule of water and the formation of our aromatic Pyrrole. So, let's continue. Instead of a nitrogen or an oxygen, if we want the sulfur, so a thiophene, again, we need to find where we're going to get the sulfur atom from, and again, we're going to have 4 carbons in the backbone, so we need a diketone, a 1,4-diketone, and some kind of source of sulfur. Well, for this, we're going to use a phosphorus sulfur reagent. So this is a reagent which has a phosphorus sulfur double bond. Several times now we've seen how phosphorus reagents are very oxophilic. So what this reagent will do is it will swap its phosphorus sulfur double bond for the carbon oxygen double bond in our substrate. And so you can see here it swaps the ketone for a thioketone. Again, following the exact same mechanism at this stage as for the furan synthesis, we can form the sulfur equivalent of the enol ketotop polymerization, intramolecular attack, and then elimination of water. This gives us the aromatic thiophene, And one of the reagents that we can use for this is Lawson's reagent, which is shown on the screen, or P4S10. So the key element of this is our 1,4-dicarbonyl, which we're getting very used to seeing now, but we need to swap out the oxygen for sulfur, and so we're going to use a phosphorus-sulfur reagent. The driving force will be the formation of a phosphorus-oxygen double bond, and so we can draw arrows which swap that sulfur for the oxygen. We form an intermediate 4-membered species that makes the first phosphorus-oxygen bond. Then by pushing the same arrows again, we complete the process and form our thioketone. Our thioketone will come and attack our carbonyl. Again, 5-membered ring is very quick to form, so this is a good transformation. And this leaves us an OH. The sulfur lone pair can come in, push that OH out, and finally we get loss of a proton to give us the aromatic thiophene. This strategy doesn't just work with 5-membered heterocycles, we can look at 6-membered heterocycles. So if we, for example, look at a dihydropyridine, again, our key heteroatom is the nitrogen, and that now gives us 5 carbons in the backbone. So now we need to look for a 1,5 aminoketone, which will come from a 1,5-dicarbonyl and an amine source. In very much the same mechanism as for the Pyrrole synthesis, our nucleophilic nitrogen will attack each one of our carbonyls, and then we'll get loss of water to form the double enamine species. However, this time, because it's not a 5-membered ring, we will not end up with the aromatic system, and we'll end up with a 1,4-dihydropyridine. But if instead of a 1,5-dicarbonyl species, we have a 1,5-dicarbonyl species with some kind of leaving group on the backbone, so here represented by X, where X could be a chloride, a bromide, an acetate, etc. Well then, at the end of this sequence, we could get the formation of the aromatic system by loss of HX. Looking at this in more detail, this time, because it's a 6-membered ring, we need 5 carbons, and that will come from our 1,5-dicarbonyl species. And we need a source of ammonia. Ammonia is a gas, so we'll have to use something like ammonium acetate if we want to use it in the laboratory. And our nucleophilic nitrogen attacks our electrophilic carbonyl. And it not only does this once, it does this twice, this time making a 6-membered ring, which is slightly slower than a 5-membered ring, but is still extremely favourable. And we can use the nitrogen lone pair to assist with the elimination of water. So we push the lone pair in, we lose OH promoted by H+, and then we neutralise the positive charge on the nitrogen by loss of a proton from the backbone. We can repeat that process on the other side, and that gives us our 1,4-dihydropyridine. So the pyridine, but with an extra hydrogen at the 1, i.e. nitrogen, and the 4 positions. But if our 1,4,5-dicarbonyl starting material has some kind of leaving group in there, so X, where X is a halogen, acetate, OH, etc., well, we can draw the exact same mechanism, following the X all the way through the process. And then in the final step, we will get loss of HX from our system and build the aromatic pyridine. Alternatively, if there is no X, we could use an oxidant that we've seen in an earlier video. What do we do if there is more than one heteroatom? Well, the system still applies. So if we look at a Pyrrole, we now need to identify the key heteroatom, but this time there's 2 of them. So we have the 2 nitrogens, which leaves us a 3-carbon backbone. So this time, we're going to need a 1,3-dicarbonyl and a source of those 2 nitrogens. And 2 nitrogens with a single bond between them, 2 NH2s with a single bond between them, is called hydrazine. Hydrazine is very nucleophilic because the lone pairs of each of those 2 nitrogens repels each other, therefore making an already nucleophilic nitrogen atom even more nucleophilic. In a similar mechanism, we activate our 1,3-dicarbonyl species with acid, and our nucleophilic nitrogen attacks. This time, our lone pair comes in and it promotes the loss of water, and we get neutralization of the resulting iminium to form an enamine. Intramolecular cyclisation of the second nucleophilic nitrogen onto our electrophilic carbonyl, promoted by acid, then completes our 5-membered ring, followed by loss of water to give us the aromatic product. So we start off with our backbone, which is our 1,3-dicarbonyl species. And our heteroatom source, which is a hydrazine. The hydrazine is very nucleophilic, and so it will attack our electrophilic carbonyl promoted by acid. This forms the first carbon-nitrogen bond that we'll need for our heterocycle. The nitrogen lone pair will halt the loss of water by breaking the carbon-oxygen bond. And then loss of hydrogen will give us the enamine. The second nitrogen can rapidly cyclize to make our 5-membered ring, attacking the electrophilic carbonyl. And then finally, a second elimination of water promoted by nitrogen lone pair. Will give us the aromatic heterocycle. in addition to 1,3-dicarbonyls, we can actually consider other molecules which have similar properties. So here, for example, instead of a 1,3-dicarbonyl, we can see that the hydrosome could do a conjugate addition to an enone. So the enone is behaving the same as our 1,3-dicarbonyl. Because after that first conjugate addition, we end up with the exact same intermediate as we've seen for this process. So it's worth pointing out it's not just 1,3-dicarbonyls that can take place in this, but also 1,3-dicarbonyl equivalents, such as enones. We can also do analysis for isoxazole. This time, instead of hydrazine, we can just do the hydroxylamine. The mechanism is identical, but now we have the attack of an oxygen and a nitrogen separately. But we can follow it through from our hydroxylamine to our oxazole product. What happens when our heteroatoms are not next to each other? So, for example, using oxazoles or imidazoles. Well, again, we can apply the same strategy. However, this time we're going to look at our key heteroatom, which is the X. So in oxazole, that's an oxygen, and in the imidazole, that's an NR group. And the backbone is going to contain a different heteroatom. So the N is built into our backbone this time, which means that instead of a 1,4-dicarbonyl or carbon species, it means there's a nitrogen in there. So if we want to make the oxazole, we can just take the 1,4-dicarbonyl directly. If we want to make the imidazole, we're going to have to take the 1,4-dicarbonyl and mix it with an amine. So this is a Robinson-Gabriel synthesis, and you can see that starting from a readily available alpha amino ketone, we can react that with an acid chloride to give us this backbone. So it's very easy to make the kind of backbone that we need. Then, if we treat that with acid, our electron-rich amide, so it's electron-rich because the nitrogen lone pair is in conjugation with the carbonyl, can attack our electrophilic carbonyl promoted by acid. This makes that 5-membered ring. Then an oxygen lone pair can come in, promote the loss of water to give us our aromatic product. So our starting materials are easy to synthesize. We have the formation of an amide. In the labs, we will typically do this with an acid chloride and an amine. But in nature, there's a lot of amide bond formations in proteins, etc. So, we get nucleophilic attack promoted by a base of our nucleophilic nitrogen onto our acid chloride. We push the electrons up onto the oxygen, then back down to lose chloride and give us our new nitrogen-carbon bond. This is our key 1,4-dicarbonyl species for our oxazole synthesis. We can draw the electron-rich carbonyl, more electron-rich now because of the nitrogen lone pair, which is in conjugation. So it's the amide, which is electron-rich, that cyclizes around and reacts the more electrophilic ketone carbon. Then our oxygen lone pair will promote the loss of water by kicking out our OH promoted by acid, and neutralization of the resulting oxonium species builds our aromatic system and completes the synthesis of our oxazole. We can continue this and look at the synthesis of heterocycles with 3 heteroatoms. Looking at a 1,2,4 triazole, we can choose 2 heteroatoms, and then that leaves us 3 atoms in the backbone. Again, this time there'll be 2 carbons and 1 nitrogen, so we'll have a dicarbonyl species with a nitrogen in the middle, and a hydrazone type species. This gives us the Einhorn-Brunner synthesis, in which our nucleophilic hydrazine will attack our electrophilic diamide. Then the other nitrogen from the hydrazine will attack the other carbonyl. And finally, by loss of water, we'll build the totally aromatic system. So it's a very similar mechanism to we've seen before, but with more heteroatoms in the backbone. We have our diamide, and we have our hydrazine. Our nucleophilic nitrogen is going to attack one of the carbonyls of our amide. That builds the first of the 2 nitrogen-carbon bonds that we need. Then the second nucleophilic nitrogen can attack the second electrophilic carbonyl, and that completes the 5-membered ring part of our synthesis. Now what we need to do is we need to lose 2 molecules of water, and we can do this by using the lone pairs from the nitrogens to assist. So the lone pairs come in, they promote the loss of OH, minus, promoted by an H+. That gives us an iminium species, which is neutralized by the loss of a proton. And we can repeat that process to give us the final aromatic heterocycle. What we've seen is several different reactions, all of which have the same strategy. If we want to figure out how to make a heterocycle, we can identify the key heteroatoms that we're now going to need to provide, and then what that leaves in terms of the backbone. At the end of our backbone, we're going to put carbonyls, and then we're going to do dehydration and cyclisation to synthesize it. Thanks for watching. See you next time.